world is looking actually to develop things, right? So the manufacturing is another field where automated robots there in the picture will take part, will be a game-changing player in the coming years. The other thing is the research and development. That's a satellite development laboratory there. So mainly in satellites, as well as in other research areas, which actually support all these activities, connected, interconnected. And the last one is the healthcare. And that's another major game-changing field where loads of mechanical engineering things happening in healthcare, and people would surprise to believe that most of the things are modeled by researchers, the activities by human body, right? So health, fitness, well-being, and growing, all these things are actually connected with the healthcare. So the future focus, the backbone of all this research, technology, design, engineering, production is in the computation, the power of computer, right? So that's where we need computational mechanics. So this is just to show you, this is a word cloud to show you the different fields of mechanics, right? So it's starting from the analytical side of things. These are the theoretical base. If you say Hamiltonian theories of Lagrangian, Eulerian, and then coming to hydraulics, contact mechanics. Somebody was there from the civil engineering. So soil mechanics is one of them. It's actually sitting within the mechanic field. Electromagnetics, statics, solid mechanics, fracture mechanics, biomechanics. So loads of things, right? Loads of branches, actually. It's a very big topic, right? When you talk about computational mechanics, it's all about this, right? So it's not possible in 1 hour to go through all of this, right? So what I have done is to give you a bit of kind of introductory taste into these kind of different topics, which I have picked from this list, okay? So that would be enough for you to actually carry forward with your kind of passion to do research and academic knowledge as a faculty. So starting with the computational mechanics, it's a sub-discipline within the applied mechanics. So this is where the theories and practical side of mechanics go into play. The modeling and simulating the natural phenomena, that's what about the computational mechanics. So with computer, with mathematics and mechanics all coming joined together. So what we actually trying to unleash is where we try to predict the powers to actually design something, right? So it's about the fluid, solids, and complex materials. So interaction between all of these combination, and that is computational mechanics, and that help actually for the design engineering team or the design engineers to design a better product and introduce that into market. So that's the idea. So computational mechanics is actually the backbone of design engineering, and computational mechanics is in the industry, we call it computer aided engineering, right? So both are similar. So when you talk about the commercial side of things, it's actually computer aided engineering or computer aided simulation. As I said before, there are 3 pillars of computational mechanics. So first of all, it's engineering mechanics. I will be explaining about this, like the static dynamics and solid fluids, etc. in between, right? So biomechanics, thermomechanics, so it's all sitting like I have shown you in the word cloud. It's the engineering mechanics there. Now, the mathematics is another pillar. So that's where you will use the partial differential equations, linear algebra, and the FEM, FDM, all the numerical methods within the mathematics. So all are required. Then the computer science. So once you develop the model, you need to solve difficult, complex differential equations. So we convert that into metrics, and then we actually do the metrics decomposition, and we do with the programming software algorithm. and all these things using the software programs to actually develop, actually resolve the model, or actually, so we basically develop the equation and then resolve it with computer science. So engineering mechanics provide the theory. So just to give you a bit of history, so started with the civil engineering, shipbuilding and transport in the beginning of the century and the last century, and like using empirical methods and classical solutions. So you might have come across that book, Rhodes Formula, Stress and Strain. So slowly the engineers developed formulas and equations to solve complex problems in these areas, right? And then aircraft came into play. So 1950s was the era of aircraft design and space race. So what happened was, so there were complex engineering problems to solve. That's the Orville and Wilbur Wright's aeroplane model. That is the 1969 Concorde, right? So that's the first supersonic aircraft, human-powered aircraft. And that is the Apollo, the Apollo mission, actually, right? So all these aero related structures, it was required to solve the complex problem, right? So environment driven, it's basically high speed, high loads and high thermal effect on these structures. Then interaction with the fluids, that's where the compressibility coming into picture, where you have local pressure gradients, etc. You have flutter, or the interaction between fluid and structures, right? So stiffness dominated, challenging operating conditions, and the people need to solve those kind of, engineers need to solve these issues. The design driven is about the strength, stiffness, about the structural layouts and balancing things, aerodynamics, material behavior, failure in between, right? So it's Saturn V rocket, actually. So, and then weight reduction. When we fly things, we need to make it minimum weight as possible, right? So that's another thing. Then advanced materials and methods as well. So all these multi-body interactions. So all these required complex kind of equations to solve multiple equations. So people started converting those kind of set of equations into programming language, right? So that's where the automation of the hand calculation started. Now, if you develop that further, that converted to metrics and then computer programming actually solving it, right? So those in the 50s and 60s, they can, the 7x7 metric solution, like using a mechanical calculator was very, very tedious, right? It's a full day job. Now, then the analog and digital computers came into place. And in the mid-50s began to increase the size of the problem. You can see that's the English electric reduced computer. That's a big shape of a shelf. You see, that's very, very chunky computer in those days. And when times proceeds and the computer size is reduced, and that the modern computation actually came into power, then people come up with better ideas in terms of equations and metrics decomposition. That's where the displacement method came into place. So people invented that. What displacement method is all about, like you try to, in equilibrium kind of terms, you try to reduce the equation and make it a form called force equal to stiffness and displacement multiplied, right? And we try to solve that displacement, and from that displacement you can work out the strain, and then using your elastic modulus you can work out the stress. Very simple. But if you look at the multi-dimensional kind of problems, these are all kind of very, very big matrices there, and you are trying to solve big matrices. And that's why we need powerful computers to solve. So this is actually the basic thing you need to understand before you start learning about computational mechanics, right? There are, of course, many other formulations, but these are the fundamental. This is the fundamental thing. So solving an engineering problem, there are three ways you can solve an engineering problem, right? So the first one is the analytical method. That's why that's what you do with your hand. We say hand calculation. You do with your hand, and maybe sometimes calculator, right? It gives you 100% accuracy, but the thing is, it's very linear. It's just hand calculation you do for sanity check these days. Now, the numerical method, that's where we need to focus more onto. This is where you try with a governing equation, and then you try to differentiate it, you try to formulate that with partial differential equation, integrate it or differentiate it, and then convert that into algebraic equations and then formulate matrices, right? So it's an approximation style of thing. So you just basically iterate your solution to come up to a better kind of number. That's called approximation with some assumptions and some sort of error management. You try to minimize the errors there. So that is a way to solve realistic kind of problems, right? But still we are not there, because the realistic problems, it's difficult to convert into mathematical model. So we try to verify the methods, doing either comparing with the hand calculation or doing experiments. So this is where you employ all these FEM, BEM. FEM, BEM is boundary element method, finite volume method, finite difference method, etc. Right? Then the experimental method to solve an engineering problem is just you take out and you do a prototype and you try to test. You put a load on it and you try to actually measure it, whatever the strain gauge gives you, or the accelerometer gives you. So the verification can be challenging and the process can be expensive as well. And if you try to do the experiment and it fails, you may need to develop another prototype that will take time and money, right? So strain gauge, photoelasticity, all these techniques are used for experiment method. So what we do these days is we try to do these all together. That's for concept design for a product. And then for a detailed design, you do a numerical, you do an FEM, and then you try to compare that with the experimental result, right? The CFD, of course, is there. The CFD is computational fluid dynamics. That's there for system design. That's where you need to get the temperatures, right? When you try to design something, you need those values to put that into the, to find out the loads, the stresses on a system, right? So they are at system level, but that's also part of the numerical method. Now, just some fundamentals. So cantilever beam there. So there, like you can see the length there, and you applied a load, and it deflects towards the negative downwards direction and gives you a y deflection. So we take that unknown, and conventionally we solve that using the equations there, right? So I hope everybody familiar with that formula. So that's the fundamental formula for finding out the deflection there. So the key here is to develop that equation and try to solve try to put some boundary conditions, right? And try to find out the solution, right? So the mathematical solution for the governing equation is to integrate there 2 times and then put the boundary conditions, and you get the results there. So you have to bear in mind, this is an idealization. Whatever people learn in textbook, it's just an idealization. In real-time world, that doesn't work. The reason is the assumptions you have put into that theory is small deflection, isotropic material, cross-section of the beam is perpendicular, plane and perpendicular to the neutral axis. The radius of curvature should be large enough compared to the cross-section dimensions, right? So that's an idealization problem. And then when you come to the real life problem, all these assumptions may not be valid, right? For example, the deflection of a gearbox. So the governing equation there, you cannot simply take that because the governing equations are complex. because your degrees of freedom or the movements in different directions of axes are going to be n or multidimensional. Okay, so that's why we need numerical methods. We need to discretize the problem. We need to just cut down into small chunk of elements, and then we apply some mathematical theory called variation sometimes, and then we try to approximate the solution and then try to improve that solution, or we call it iteration, right? Minimize errors, and then we find out the solution. So this is required when the problem is very real and multidimensional, right? So the key here is the approximation there. So basic approach is like you discretize a domain like that, and then you put the boundary condition, and then you put an approximation function for the displacement there, right? So what it does is it's actually spins the coordinates there and gives the displacement based on these coordinates. So we call it interpolation function or shape function sometimes, and this is the fundamental theory of meshing, right? So we calculate only on limited number of points. They are called nodes, and then interpolate across those nodes. You can get, and using these external boundary conditions or the constants, you can get the values for the displacement, and we approximate it, and then we try to improve the equations, improve the results by either increasing that sort of relationship, maybe higher order with a parabolic or more hyperbolic or kind of relationship to actually approximate the domain. It could be a domain of force or stress, anything, whatever. So we try to approximate that to find out the displacement. So the displacement gives you the strain, and then from the strain, you put the elastic constants or plastic constants there to find out the force. So that's what the software does. That's what numerically you need to solve the problem. Now, computational current process. So just to show you what's actually happening in the numerical method or the computer engineering world is where the current method is you put some engineering data, product knowledge and experience will go into the preprocessor and the CAD geometry that combine, and the preprocessor gives you some sort of text file, and that's integrated into the solver, and solver mathematically, so numerically decompose the metrics and solve the problem, and then you get some results, and that result will be taken by the post processor and then taken by the it generates a report. So that's the idea. Now, that is important because that is where the key things are happening. So going to the future, that's the process we may need to follow in the future. So this is where the pink color there, they are actually repeating. So these are the iterative. For the design engineering, things are getting iterated. So it's automated as well. So starting from the maturing of the design, putting the engineering data, they are actually inbuilt in the system. Experience, all are computationally inbuilt. And then these cycles will take place. And you can see the iteration take place in multiple stages. So this is what the ideally in the future looks like. You put a problem, and the system picks up the product knowledge and experience and the engineering data, which is inbuilt in the computer system. And using the CAD geometry, you develop the results like that. And then it iterates to get the best solution. So if you talk about the methods, the numerical methods, first we need to think about the discretization and the discrete methods there. So the first thing is the finite element method, right? So we use that for structures, as I have shown before. The force equals stiffness multiplied by displacement, right? So that's the mantra of finite element method. It gets the displacement out, and then we get the other results. So applications: linear, non-linear, buckling, thermal, dynamic, electromagnetics, and fatigue analysis. And there are other analyses as well, which can be compared as which can be done. Even the fluid dynamics can be done solved with the finite element method. The boundary element is where the boundary actually discretizing the boundary. So that's another discrete method. So it's used in acoustics and noise, vibration, harshness. So it's mainly in automotive and civil engineering field. FVM is the finite volume method. So it's similar to the finite elements, but here the element is the volume, right? So it's where the pressure, velocity, area, mass, etc. are important. We use finite volume method. It's basically looking at the try to discretize and resolve the Navier-Stokes equation sometimes. So fluid dynamics is the main application there. Finite difference method, sometimes we use CFD fluid calculations in finite difference method as well. Thermal engineering problems as well in finite difference method. So approach is based on the Taylor series, and it's easy to program as well. So just to give you a bit of idea about the analysis type, so I think most of you might have familiarized with the governing equation there, right? So mass, damping, stiffness, and the force function, right? So the problem we solve will be mainly with respect to that equation. We try to decompose into that formulation. And then if you come to the linear static, that's where there is no mass, there is no damping, and these two things are constant there. So that's linear static. The reason why it is linear is because these things are constant there, and we don't have any sort of variation in time or anything like that. And the reason why it is static is because the loading condition is zero or it's at equilibrium state. Whereas the structural analysis is where all these things, so dynamic analysis, buckling analysis, all are basically structural. If you talk about the nonlinear, this is where the things can change with respect to the force applied, plasticity, hyperelasticity, and creep. They are material non-linearities, right? Stress stiffening, large deflection, large strain, they are geometrical non-linearities. And there could be contact surfaces where the boundaries or the friction kind of contacts where the non-linear static analysis, the non-linearity is actually there with respect to these kind of phenomena. You can look at the function like the difference between the linear and non-linear is where the K, the stiffness, is actually a function of the displacement. Then you have the conduction, convection, and radiation, which actually sits within the thermal analysis, so cooling and ventilation mainly. Stress life approach, that's the fatigue. So strain life, fracture mechanics, power spectrum analysis. So these kind of related with the fatigue failure and also the fracture mechanics failure. Again, that's part of the numerical solutions, numerical methods. CFD is where we look at the fluid statics and fluid dynamics, similar to the mechanics there, but here we are solving, similar to the structural analysis there, we are solving the fluid problems. Crash analysis is it's actually a subdivision of the dynamic analysis, where there are automotive standards, there are aerospace standards. We need to look at the passenger safety, occupant safety. So that's where we need to test. The experimentation is very expensive if you try to crash an automotive, right? So that's where the simulation, which actually replicate the crashing of the automotive or the product, and then assess the crash worthiness and impact simulation, drop test simulation. So these are all fun simulation, but you need very much knowledge to do that. Nvh analysis is the noise vibration or vibration there is, it's actually coupled with acoustics, right? There. Now, there are analysis which are subdivisions of or combined with non-linear and dynamic analysis like rotordynamics, multibody, bird strike, all are actually coming from nonlinear dynamics. So they are the main ones I have listed there, and we will be looking some of them. I believe I missed talking about the optimization. Again, that's another technique. Actually, optimize the design by a discrete approach, like to the geometry and optimize the geometry. It's basically aiming to improve the design. Now, numerical methods here. So for nonlinear analysis, so that's a plot with force and displacement there, and that's the curve of nonlinearity. What the computer does, or what the software of what the numerical method is doing, is actually iterate, assuming a value for the displacement, iterating it many times, right, and find out the stresses, try to look at the convergence, right? So convergence is basically error. So that's the equation you need to follow. Just bear in mind the linear analysis, that's the governing equation I have shown you before. There are different numerical methods or approach to solve the differential equations. Whereas over here, you can see the iteration will take place, and there is one thing called time stepping, right? So we assume a time step, that's the difference between the time intervals. And then the system will actually try to solve it by converging the solution and then do again, right? So this is the matrix decomposition taking place in a nonlinear analysis. And one example is the Newton-Raphson method, right? So extensively used in nonlinear calculations and contact calculations. Now, one thing to notice, though, is about the types of methods where implicit and explicit methods. This is types of different kind of iterations we follow in a numerical analysis. So linear static normally uses the implicit kind of type of numerical method. So this is where we put large time steps, more than that value. And then it's for normal kind of solutions like linear structural calculations. We do that with the Newton-Raphson. Now there is explicit method. So this is where high impact or high speed impact problems, where we, like nonlinear dynamics, we use the explicit approach. One thing to notice, though, is here the main factor is the stability, right? Try to converge things. Now, you can see the time step there. So no convergence. So there is no convergence. There is a kind of thing called stress or singularity. So what happens is the stress can be infinite at some locations when it iterates, right? So it's so when there is a non-convergence, so it goes into stress singularity where the solution become at an infinite stage. So there are some techniques to overcome that, but just bear in mind about that. I think that's about the basic idea I have given. Now I'm switching into the commercial side of, or the industrial side of the computer engineering, computer-aided engineering, and also the computational mechanics. So the main users here are the aerospace, medical, military, and automotive, right? So you can look at there, the worldwide number. This is an agency who actually picks the data. For 480 computer-aided engineering software providers. And you can look at the revenue it generates is 6 billion, right? And the forecast for 2027 is 14.9, 15 billion. It's going to be doubled, more than doubled, right? So that's the size of the industry. The reason is because people are tending towards more computer-powered simulation, and the more computer power means we can simulate the real condition more realistically, right? I'm not talking about the different sectors there, but just to bear in mind, these are the main players like ANSYS, Siemens, the Dassault Simulia. Then you have Altair and Hexagon. So they have actually evolved years and years of kind of in the industry. They were in the industry and they were acquiring different companies. For example, the CFX and Star CCM are the leading players in the CFD simulation, and these two companies actually holding both of them. You can see the NX Nastran is one of the main structural backbone of Siemens package, whereas ANSYS itself is the main structural package there. So these are the main industrial players. So just to show you, just wanted to show you the size of the industry there. Now, if you look at the where we actually try to resolve problems, you can see it's everywhere. So it's coming from like aerospace, defense, high-tech machinery, services. I'm not going to read all of them, like fluid, failure modes, plastics. We will touch most of these areas in my later slides. So the forecast, as I have said, if you look at there like FEA, CFD, so FEA is the major player. The reason is because FEA is a must thing for designing a thing in mechanical engineering or any engineering. FEA, we do FEA for structural strength, stiffness calculations. CFD is, as I said before, it's a system level. We need to find out how the object behaves in environmental conditions like fluid interactions or heat, thermodynamics, etc. Multi-body dynamics is where the interaction between the bodies, so it's actually sitting within the structural dynamics world, but multi-body. I have another slide for that. We'll come to that later. Optimization simulation is where like simulating the realistic conditions like environmental or simulating manufacturing process, for example, these kind of things. So eliminates the need of multiple prototypes. As you can see, 2027 projection, it's an unprecedented growth there. The other thing is about the battery enhancement. So EVs, electric vehicles are into the picture, and I think the future is electric basically. So the battery modules needs to be developed and more efficient systems in electromechanics needs to be developed. That's where people are very much focused in CFD and simulating these in real-time scenarios. So I have a slide, I think 2 slides for the technology forecast. So this is basically industry-based. So if you look at the defense and aerospace, the main thing here is to, if you look at the defense, it's modernizing the old structures and systems and security, surveillance, turbo propellers. That's another interesting field. So jet engines will be replaced with propeller powered aircraft. E-fan, that's electric fans, pure electric flights, high temperature materials, ceramic matrix composites. So these all are within the aerospace industry. So these are the developments happening in the aerospace and defense. So passenger safety as well. So computational mechanics going to play a big place there. Automotive, like again, the passenger safety and driver interactions. And these days we are talking about the driverless cars, semi-autonomous cars. Noise, vibration is another thing. So electric vehicle research as well. So all these are going to be simulated as well. Electronics. So this is one of the areas where very few attention took place in the last few years, but it's emerging, right? It's an emerging market. The mechatronics and robotics as well. So the wearable devices, for example, so and the electronics like high visualization techniques, for example, like the dynamic range, illumination. So electronic device development is a major game-changing field where computational mechanics is going to be applied. That's a circuit box, actually. Now, healthcare, you can see that's a dental simulation, right? So medical devices, so the engineers started working with doctors these days, and bone fracture, for example, dentistry, medical imaging, So all these cardiovascular chronic diseases developments are taking place in these areas. It's both, the interesting thing is the research as well as parallelly industrial or commercialization of these is also taking place there. The other thing is the additive layer manufacturing, so casting or manufacturing automation, for example, all this simulation is taking place. So that's in the coming few years. So this is another emerging market. Satellite technology, so private space technology is emerging. So space structures, orbital, like rovers, for example, and debris, like waste recovery from the space. So all these needs to be simulated. I think that's about the technology forecast. There are many things because we have less in time. I'm just concluding there in terms of commercial aspects. Now I'm slowly trying to switch my kind of pitch into the presentation towards the research side of computational mechanics, right, and the future scope. First one is the computational fluid dynamics. I know there is another session for computation fluid dynamics, so I have put only one slide. That's this one. So it's basically prediction of fluid flow. As you can see there, that's a multi-phase flow. That's multi-phase, basically. That's simulated. Over there, it's the vorticity, or the turbulence there, again simulated with the computer. This is the turbine cooling with that sort of thermodynamic interaction of the blades. So it's high temperature material as well. So it's all about flow, pressure, fluid pressure, temperature, all these things. So FDM, finite difference method, finite volume method, finite element method, all are required or are being used. Another interesting thing is the fluid structure interaction. That's where the interaction of the fluids on the structure. This is another area within the computational mechanics. It's within the dynamics as well. This is where these interaction are simulated, right, with the fundamental theories like Eulerian Lagrangian approach. It's very important in industrial design as well, in commercializing these aspects, because the aerodynamics in the aerospace world, the structures needs to be simulated for the unprecedented or the unpredicted loads. That's where fluid structure interaction is important. The other one is the rotordynamics. So you can see any rotating machinery. There is a rotor and a stator, and there is a shaft, then bearings, couplings, everything inside. So what kind of complexity it has is it can deflect and it can wobble. And the forces coming into picture, there are inertia forces, there will be Coriolis forces, and that causes the shaft whirls, right? So the important thing is like finding out the critical speed and modes, and then the out of balance response. The challenges here is like the rotor could be flexible sometimes, and there could be bearings which we need to assume in a real-time scenario. They are non-linear in itself, seals, coupling, etc. So as I said, the flexible rotors there, you can see the blade, that's a disc attached with the blade, right? So we call it blisk. So that is flexible and that's rotating. That's the issue. That's the challenge here. Stationary, coupling with the stationary and rotating. So there are stationary structures within that system. Modeling centrifugal loads, fault diagnostics, and condition monitoring as well. So the things are in service and that needs to be monitored, and that's also by simulation. Another area is multi-body dynamics. As you can see over that picture, we first of all do kinematic simulation there. And then we try to find out the deflection. We try to get the velocity and the other things, the inertia loads, etc., out of that displacement, velocity, and acceleration. And then we carry out a dynamic simulation. This is another emerging thing. So forward dynamics means you apply the external force, and inverse dynamic is where you do the analysis of forces to try to find out the kinematics within that. That is within the dynamic simulation itself. So extensively used in the automotive, and it's emerging as well. And more, we need to solve many problems in real world scenario. Commercial software is another Adams MSc software. Another one is Recurdyne. Other dynamic problem is crashworthiness and passenger safety. So this is basically to certify if you try to manufacture a car, you need to, that needs to meet the regulator, the regulation needs by the government, right? So that's where you need to certify it. So for that, you need to do testing. So the real world scenario, that testing is very expensive and costly. So that's why we need to do simulation. So in this, we have everything appearing in that equation that we are trying to solve. So there are things like collision dynamics. That's why it is solved. It is actually solving and just replacing the full scale test. So it gets the displacement, velocity, and acceleration, and then we convert that into stresses, plastic strains, forces, impact, energy, etc. It helps to make safer and more reliable vehicles, but the challenge here is the high computational cost. So this is basically mixing two kind of approaches. So one is Eulerian, that's where your meshes or the system will be fixed. And Lagrangian is where the mesh follows with the deformation of the material, right? So mixing that, it gives you, try to help you formulate that. And we adopt the explicit numerical schemes to solve like the central difference technique. Another complexity here is the nonlinear contacts there. So it's high, you need to realistically approximate the friction phenomena, contact phenomena there, like penalty methods, Lagrangian multiplier, health theories, and it's getting very complex when it gets into the multidimensional kind of interaction there. Bird strike analysis, another type of crash test. You can see birds going into there. In the old days, what we do is we try to simulate that in the real world scenario. We take the engine out, we put the goose into the blades, right? So these days, the simulation is more promising and more predictive results we are getting from that, as you can see in those animations there. Again, it follows the same approach what the crash test does, adopting the Lagrangian Eulerian formulation. You get the displacement, velocity, and acceleration, and you get the rest of the things out of that sort of results of that numerical decomposition. So here the mesh domains changes arbitrarily, so to take up the shapes of the deformation, and that's what the Lagrangian Eulerian formulation does. I don't want to talk much about the theories there. This is what happening in the background. So the meshing advancements. So this is another important area. So there are different types of techniques to actually do meshings. I will show some of the things in my next session when we do the machine design session, how to mesh things like that for a design engineering purpose, but for research purpose, that is important. And you can see in any numerical techniques, 80% of the analysis time is actually spent on the practical engineering problems is about meshing. So there are people who are researching in trying to improve that. And these days, meshless techniques are emerging as well. So isogeometric analysis, where when you modify the design, the mesh is not going to be changed. So it changes automatically. So it actually stick with the geometrical shape. And reverse meshing is where the mesh actually defines the CAD geometry. Okay, so techniques, different techniques. Strain smoothing, it's a bit more complicated. So it's basically within the formulation, within the theoretical displacement formula or the approximation of the shape function, we actually put additional kind of parameters within that equation for mesh distortion. So I didn't talk about the mesh quality parameters like distortion, skewness, these kind of parameters like skewing. There are some mesh quality things, and those parameters I'm talking about. So we put that in the approximation technique, and it's especially useful in composite modeling because that's a multi-dimensional variation, isn't it? There are no isotropic. Multi-block structured meshes. These are like you mesh block by block and then try to map it for complex geometries. Adaptive mesh refinement, I got a video in my next slide. So this is where you try to resolve we try to refine like the areas of interest while meshing, right? So that's what it is. I think I can explain that in that picture. So basically the singularity means when you cannot resolve the system, the iteration fails, where you got infinite amount of the stress value it can show. So to avoid that, adaptive mesh technique adapts with respect to the local regions where you need fine meshes, right? So that's what adaptive mesh refinement. This is metal cutting technique. It's actually simulated, and you can see the ALE technique here as well. The arbitrary Lagrangian Eulerian technique here, because the mesh also changes its shape when the deformation take place. Okay, so two things there: adaptive mesh refinement as well as the ALE method. Polyhedral meshing, it's a bit more like enhanced version of the normal 3D meshing. You've got more nodes and more elements, more surfaces, and it's especially used in conjugate heat transfer or CFD. So conjugate heat transfer is where you try to simulate the CFD first, and you get the temperature out. You put that in the thermomechanical simulation to find out the creeps, displacement, etc. Right? Polyhedral in a 2D, it's hexagonal, whereas hexagonal, octagonal for 2D elements, whereas for 3D, more phases like that, like a football shape, you see. So it actually, in approximation, for the sake of approximation, the gradients can be well approximated between the pressure gradients, etc. Mesh quality as well can be improved in polyhedral technique. So now the another advancement is about meshless FEM. So some of you have heard about the P element technique. So P element is like you try to make the coils meshed there. So convergence to actually enhance the convergence to get the easy solution. We adopt that technique, and I think it's mainly at the concept stage. It helps the design engineer to understand the key areas for loading. So it's an emerging technique, and it's basically borrowed from the Galerkin FEM variation principle, right? So basically what meshless is like, it's a nodular rather than elemental kind of theory. We try to focus on the nodular, or based on the nodal interaction. And how it interact with the other nodes. It has tremendous potential. The reason is because of the easiness, because as I said before, 80% is spent on the meshing side of things. So we can avoid that sort of process if we try to find out a solution without meshing, right? So element-free Galerkin, what we call for the proper method, but there are other techniques like volumetric meshing. I think that's volumetric. So we approximate a large element there, and that will actually develop the other elements in the boundary, right? So then it goes into a method for meshless kind of approximation. There are proprietary methods these days. So SimSolid from Altair and ANSYS Discovery Live, they have proprietary methods. I think that one uses ANSYS Discovery uses volumetric method. So what it does is you can get this solution within few seconds, and that's more than enough for a design engineer to look at that, to look at the structure and look at the areas of critical areas, and then he can redesign the component, or he or she can redesign the component. So that's what it is. And the technical advancement in the coming years will actually get that borrowed into the software, and that's an interesting area for research as well. Extended FEM or extended or generalized FEM is where we borrow the theories of Ted Belichko. He's a revolutionary. He was a pioneer in the discontinuous problems in FEM, right? So basically, what I told about the singularities, where you go, you come to a point where the stress getting infinity, and you cannot solve using a numerical approximation. We try to avoid singularities. So it's the singularities mainly occurs at highly concentrated areas or locations, especially for a crack, simulating a crack. So you can find stress concentrated areas. And when you try to solve with normal technique in FEM, you won't get there, right? The reason is singularities will poke up, like, and then you will have high peak stresses, and the system won't sustain. So that's where the extended finite element comes in. So what happens here is we put that in the formulation, excuse me, and we put the some sort of enrichment functions within the approximation functions, and that takes it to smoothly solve the problem, right? So crack propagation modeling, where we try to model a crack by simulation. What it gives you, it avoids the mesh refinement. So it avoids the refining the mesh in each iteration, so that there is no singularities coming in between. So you try to get solve the problem. So the problem, also the boundaries as well, you can solve that, and holes, inclusion, so casting defect, for example, porosity, all these areas you can actually employ the extended FEM or generalized FEM method. So now I have to show you the research direction. So I got a few more slides with respect to that. So first of all, I think I have talked to you about the virtual product design. So the product design is where FEM is extensively used. So these are the areas for research as well, like ergonomics, life, passenger safety, acoustics. So all these areas where the research taking place nowadays. Multiscale modeling or multiscale phenomena is another research area. Like that's another formula. I got another slide for that. So it's sitting within the material science, but the scientific principles are borrowed from the continuum theories. It actually clubs the quantum mechanics with the macro scale mechanics, and then try to balance that to get you the results. Model selection and adaptivity is another area of interest these days, because when you get an engineering problem, people are confused which kind of formulation or what kind of modeling approach or for model for error estimation as well, or convergence we need to adopt for solving a problem. So that's why we need model selection adaptivity choices, and automating that is a big step in the computational mechanics. That's another research area. Parallel computing, I think most of you have familiarized with the supercomputers or high performance computers. So when you have large scale problems, large simulation, for example, simulating the weather condition or glacier or ice modeling or something very big modeling, it's not possible with normal workstations. For a jet engine simulation, for example, it will take a month actually to solve in LS Dyna to solve the fan blade of the containment exercise. So I will show a slide about the containment in my coming slides. So these kind of things, very big kind of bit requirement. So that's why parallel computing is an area of research. Biomedical application. So this is where you have predictive surgery. For example, before the surgery, you try to do a simulation for that surgery, like flowing the blood and doing the CFD or the blood flow, for example. I got another slide coming for that as well. And then try to apply the mechanics theories there in cells, bones, nerves, etc. So there it's a simulation for cigarette smoke inhalation in the lungs, right? So this is a computational fluid combined with particle dynamics. The mechanics we apply in the particle dynamics and we combined. So big research going on, like the inhalation, chronic disease like asthma, for example, going on there. So you can see fantastic results, if you try to research in these areas to get that sort of, and there are lots of research funding in medical and healthcare field as well. Other thing is stochastic modeling. So this is where you put the probabilistic kind of things in the uncertainty to actually control the uncertainty. For example, when a flight flies to the turbulence of the wind, and you cannot predict the way the wind comes and the random effect of the wind going into the structures like wind turbine, for example. So that's where stochastic modeling is required. Environmental issues are solved in probabilistic method. Error estimation is another area of interest where we try to look at the convergence, the numerical kind of approaches, and look at the effectiveness of these methods in reducing the errors, right? So the other thing is the environmental changes. So here, like as I said before, the atmospheric changes and ocean currents, so subsurface reservoir modeling is where the oil field, the flow of oil under the subsurface are actually simulated, right? Water, gas within in the cavities underneath. So this is how the reservoir modeling looks like. So these are all funded by Middle East companies actually looking at, try to simulate the real scenarios, simulating the real scenarios. Composite materials, I'm not going to talk much about that. It's the three-dimensional kind of property, so the changes in the property of the materials, and primarily in aerospace and automotive, these research are going on. Unsteady turbulent flows, multi-phase flows, all these are sitting within the fluid mechanics, so fluid mechanics research, as well as fluid dynamics, computational fluid dynamics. The satellite technology like extraterrestrial events like supernova explosions or galaxies, etc. That's a core mill simulation, and that's a multi-phase modeling. So this is how that's a multi-phase flow, so multi-scale modeling is where, if you look at the, so there are areas like within the material science, things like fluids, solids, polymers, proteins. You need to apply several theories or several models, right? So in different scales. So scale means the size of the object. So in normal condition, we use the macro, we put the macro scale finite element approach, right? Whereas in some things like proteins, for example, you need to use both macro scale and quantum scale. So multi-scale modeling is basically approximation in spatial and temporal scales. It's a study of complex objects or complex materials, and then bridge the different approaches together, right? Macro scale and the quantum approaches. So it's basically the constitutive laws, like the Hooke's law, for example, may not be valid when the thing goes into the quantum scale. So there you need to put the quantum approach. So combining that with the molecular dynamics, continuum mechanics, etc., are you then look at the balanced kind of approach and then combine that together and then try to solve that analytically. Chemical phenomena like chemical reactions, diffusion, etc., are also within that. So biomechanics and predictive surgery, as I said before, blood vessel simulation, right? So when a person going into a bypass surgery, for example, the simulation can take place on that particular patient, and blood flow, and there would be several options available for the oxygenating the blood cells, and then they will be simulating that, and then they give different options to the doctor, and when the surgeon does the surgery, he can look at the various results there and try to get the optimum or what's good for that patient. He can apply that sort of thought process in that. So how we validate all these models is by MRI scans or blood flow testing, etc. Orthopedics is another area where you can see the damaged like replication of the stents within the bones and the joints there. So that's the corpus joint. So again, that's a big area, big players there. Both industrial and research is going on there, fracturing as well as the functional and non-functional kind of human bones, etc. So that's all about the research direction. Now I need to talk about something about the challenges there. So first of all, any sort of method, the accuracy is most important factor, right? So when somebody does the numerical solution or numerical analysis, whether it's by programming or by software, he or she need to be absolutely sure that results should be valid, right? So that's what we try to validate the method. So these days, what's happening is models are tuned to testing. So there will be a set of laboratory environment, and then people test it, and then you validate that with the computational method. The problem with that is it actually eliminates the realistic kind of parameters, right? So that's a challenge. So that's the challenge the researchers are focusing into, like to get the realistic things into the modeling and validation and verification of the results. So this is a testing. That's the containment testing. So that's the fan blade of and when the jet engine rotates, we try to inject the blade into that composite structure and try to look at the impact energy and whether it's safe or not, whether it can contain that blade event. Okay, so that's very important for certifying an aircraft engine or a jet engine. So the reason why I'm showing this is that engine costs around like 3 crores. I think it's 3 crores maybe. It's more than that sometimes. So it's very difficult and it's very time consuming and very expensive. So the way to do that is doing experiment, and then we validate that. And then when there is another engine, they can only do that method, right? They can do that simulation. That actually, the method can be validated with one experiment, but then going into the future, the challenge is to try to replicate the realistic interaction there into that simulation. And then try to simulate it realistically. So this is another example of bird strike or crash test, all right, putting the ALE approach there. So physical phenomena replicating into modeling is difficult. Examples like single crystal casting, burning, multi-phase and change of phase and fracture, and spalling, stochastics, etc. So another challenge is integrating this, right? For example, emerging things like imaging technology, tomographic visualization techniques are emerging, and how we cope, I think the computational mechanics cope with integrating that with these areas. And the disciplines as well, like quantum mechanics and molecular dynamics, and these are all interactive these days, and biomedical systems. So integration is an important thing. And if you look at the biological system, the material are all different, like they are all non-elastic, elastic properties, and very much non-orthotropic materials, right? So study of microscopic phenomena is important. The study of those tools are important as well. So engineering materials needs to be enhanced to accommodate the biological materials, tissue engineering examples, for example. So radically new computational tools needs to be handled with the multiscale phenomena, heterogeneous materials, discontinuous behavior needs to be studied properly, and fracture mechanics, another area. So automating all that phenomena into numerical approximation is important. Now, I think there is a session for open source coding environment. So I just wanted to show you the open form there. So it's a C++ toolkit actually developed for customizing, because it's an open source and it's an emerging area where very good simulation capabilities are there for continuum mechanics problems, right? So it's Linux based. It's emerging, so the large enterprises need to cope with that. First of all, cloud computing, this is the future. So this is where the simulation can take place in multi environments, in multi systems, and it's web-based interface where, for example, in a COVID situation, people can sit anywhere and work onto the simulation using cloud computing. So hyperconverged infrastructure is a platform for that sort of technology, right? Similar cloud there, ANSYS cloud. So the big players are coming with solutions for cloud computing within the simulation environment. High performance parallel computing, I have told you before. If you look at the capacity of computers, you look at like 10 trillion operations, right, in these years. So that is a 10, is that 10 lakhs? I think 1 million degrees of freedom. Material geometry conditions. So these are all making the problem complex. So many equations to solve, but the enhancement of computer is an advantage, and the parallel computer will help to look at the realistic problems. That's an IBM Blue Gene supercomputer, 64,000 process core. It's a room size, right? That solves the simulation, the realistic current day simulation. So I'm just ending my presentation with that. So high performance computing, IBM developed commercially that when any enterprise can buy that, actually developed 2019. So quantum computing, what it says, so it's super efficient in solving engineering problems. And that's the emerging technology. And in few years of time, you can see one of them in a leading manufacturing company, most of the leading manufacturing companies, I believe. So that is it. So computational mechanics, it offers a greater understanding and advance in the modern science technology, especially in the environment, personal health, safety, and security. That's the future direction. I think I forgot to add the electronics as well. Physical and biological system, multiphysics, we simulate that. There are educational challenges, right? So the reason is because the computer is advancing, the parallel computer capacity is advancing, but educational, if you look at the textbook, it's all about idealization. And in the future, what students want to learn is the realistic simulation. So because of the emerging computer power, that would be easy to solve realistic simulations rather than idealized models. Okay, so that's the challenge. So that's where faculties need to look at teaching students the realistic simulation. So the global collaborative communities emerging. So multinational initiatives are emerging in computational mechanics. So I hope and I'm sure that in the future we all work together. We will be working together in computational mechanics. So that's all about the introduction and the scope and future of computational mechanics. Thank you very much for listening my session. And I think I have gone up, I think 10 minutes above the actual time. So if you have questions, you can ask now. I don't know what's the plan for the next session. If somebody taking, Abu Bakr Sar is there. So I just finished. So if you have questions, you can ask, and I will wait to listen from you and the organizers, Abu Bakr Sar as well. Yeah.
Thank you, Halim Shah.
Yep.
Nice
Thank you, sir.
presentation. You covered a lot of information.
Yeah.
So questions from audience, please. So Halim Shah, there are a few questions in the chat box.
Okay, I can have a look now. Give me one.
One question is from Dr. Santosh Mishra. Is there any separate classification for fluid structure interaction?
Is that question for the programmers, or is that question to me? Is that separate? Do you mean is that a separate program, software application, or is a separate training program? Do you mean it's a software package, or do you mean the training program, which in this training program you are expecting a fluid structure interaction session or not? I'm a bit confused about your question.
The question is from Santosh Mishra. Dr. Santosh Mishra. Are you on?
Dr. Santosh Mishra, you can unmute and ask your question.
Okay, a couple of questions there about software packages. Can you suggest any software packages?
Okay. Yeah, I got it. So the fluid structure interaction, normally we use LS-DYNA for that kind of fluid structure interactions, fluttering, etc. ANSYS CFX clubbing with the structural package of ANSYS. I mean, LS-DYNA is actually with ANSYS these days. So NASTRAN as well. So these days, coupling simulation can happen. So irrespective of the software, what we use, basically we do a CFD, and parallelly we try to couple that with the structural analysis, and that's what fluid structure gets you.
Okay, any other questions?
I will have a look at the chat box. I'm struggling to find out the, right, okay, I can see the chat. Is there any question I need to answer in particular? Any software you suggest for computational simulation? I believe in ANSYS because it has a comprehensive package, right? But though there are, so US-based industries use ANSYS extensively, but European-based industries use Simulia, Abacus, what I have seen. But ANSYS, for structural simulations, ANSYS is a recommended one. But having experience in different software is very good. So if you have an opportunity to learn packages, try to learn everything. But start with ANSYS, I recommend, because there are many training materials available in YouTube and online about ANSYS. And ANSYS is free downloadable from their website for academic purpose. So ANSYS is a good start, I believe. PPT I will discuss with Abu Bakr Sar. I will be sending a copy to him so he can follow that. The biological flow simulation, yeah, that's within the fluid CFD actually. So I have shown you an inhaler example, the lungs inhaling carcinogens, for example. So we simulate that in CFD packages. So that's what it is about the biological flow. Thanks for the feedback. I hope you enjoyed. So I'm just looking at other questions. Which software best for thermal analysis? Again, ANSYS is good. CFD, CFX is also good. Thermal means it's advection, convection, etc., isn't it? So it sits within the multi-physics of structural analysis software. So if you go into Simile Abacus or within ANSYS structural, you can solve a thermal problem. Excellent presentation. Thank you for that information. Yeah, a good presentation. Lot of nice. Yeah. If there are any separate classification for fluid structure interaction, yes, it's a separate subject because it's in aerospace we call it aeroelasticity, right? So aeroelasticity is where the fluid and solids interact each other. So it's a separate subject and it's emerging. So if you have a good opportunity to learn that, try to learn because that's emerging and that's going to be a very big industry in the future. Okay, I think I have gone through almost all the questions. Thank you very much. So I'm passing over to Abu Bakr Sir. I'm just going to stop share now. So it's up to you, sir.
Thank you, Halim Shah. So we are eagerly waiting for your second session. I think it is on 6th.
Okay, thank you.
Okay, welcome.
Okay, so thank you. I'm logging off. Thank you very much. And
Start at 11:30 a.m. So